Hello everyone, this is Sebastian, and today I'm going to keep talking about the book Deep Learning Architecture, a mathematical approach. And today we are heading into chapter 3 about cost of functions. So today we will talk lots of things on cost of function, what is cost of function, how cost of function works, and introduce you some basic type that are normally used in neural networks. So let's begin, right? Today in our video, we got full part introduction. We will talk about what is input, output of neural network, and what is the target of a neural network. And following that, I will introduce you some error functions, cost functions we call supreme error function, L2 error function, and the MSE mean square error functions. So we will talk about how they looks like each other and how they work and why they are useful, why so many mathematicians and computer scientists try to use this cost of functions to solve our solve most of the practical problems in our daily life, right? So let's begin introduction. So introduction, what is input? The input of a neural network is a variable. So, first of all, it is definitely a variable because you will input different things into the neural network. And it can be one-dimensional variable, such as a number, 0, 1, 2, 3, 4, right? Or vectors, for example, like 0, 0, that is original point of or say like 0, 1, 2, 3, a pair of vector that is in R4. So generally saying a vector X that is in Rn, a matrix or random variable X, the capital X, and in general, the input can be a tensor. So a tensor is the input of the neural network. As you may know, that there is a famous package of there's a famous thing you can utilize when doing the neural network things, when coding, when building up a neural network, is the TensorFlow. I don't know what is the team that creates TensorFlow thinking, but I guess maybe they want that tensor input tensor to flow in the neural network and give you some kind of output. Maybe that's the meaning of its name, but I don't know. What is a tensor? Actually, the book gives some description. So the description is this: like let I1 to In be subset of natural number. So they are the set of natural numbers, and consider the Cartesian product, which will create you a vector, a pair of numbers that say like I1 times to times in equals to I1 in, and each ik is in the corresponding capital I, with k is between 0, 1 and n. So then a set of objects indexed over the multi-index I1 over In is a tensor of order n, and most of the time we written it at the t I1 in. So that's a little bit abstract. Most of the time I will try to give you some more realistic example, but here, because we won't use this a lot in the following part of this chapter, so I decided to delay it a little bit, and when we really need the character and the properties of tensor, we will give a more detailed and precise definition of it and some better examples. All right, so for now, you just need to know the input can be these kind of things, and generally saying it is just a tensor. So after seeing the input, let's look at the output. So, the neural network is just like a function mapping from input to the output. And so if input can be one-dimensional, can be multi-dimensional, can be vector, can be matrix, can be random variables, capital X, then you know, okay, of course, the output can be one-dimensional and or vector from or n-dimensional vector or matrix or random variable. So in general, the input can be a tensor. So the output can be a tensor, so still TensorFlow, a tensor flow in and flow out a tensor. That is amazing. And the input from the input to output is a mapping, and we call that input output mapping is FWB, and the parameters WB are the internal parameters. Basically, we just want to adjust W and B to achieve some goal. So you know y equals to fx, or the vector y equals to f vector x, or the capital Y equals to f capital X. That is how neural networks neural network works, right? So this is the input-output mapping. This is what happens through the neural network. And then once we know, okay, what is a neural network and how it works, basically, we talked before, it is just a function approximator. It is just an ultimate approximator that we expect it to approximate almost everything in the world. And so there must be something we want to approximate. That is what we call the target function. So what is the target function? The target function is the desired relationship that the neural network want to approximate. Okay, this is really clear. And this target function is independent from parameter W and B, and it is denoted as the phi x, basically. So I know there is something, but I just don't know what it is. And sometimes there may be some mixture, such as z equals to f vector x, that represents the input is a vector while the output is a one dimension. For example, when we first learn about the neural network, most of the professor and your instructor will tell you, okay, let's do a first project. We call it recognize the handwritten number or whatever. Basically, you are going to use a database we call means that contains lots of square figures of handwritten number, and it contains the scale, the gravity scale of each pixel from 0 to 1 on each place. So, you know, basically, we wanted the neural network to do is to recognize a figure and to output what is that number. Say that I gave a random written number, and the neural network need to recognize, okay, this is 9, this is 8, this is 5, this is 4, this is 0, this is 1. Basically, that is what we expect the neural network to do. So, you know, there are several pixel, I can't clearly remember, but I believe it's 28 times 28, 28 by 28. That is a 28 by 28 figure. So there are 28 times 28 pixels, you know. That in that sense, it will be a 28 by 28 square matrix, and that is definitely the input of the matrix. And what are the desired output? The desired output is just a 0, 1, 2, 3 until 9, until 8, 9, right? So the output is one dimensional. That is when some case the output is one dimensional, but the input is a matrix. So that is an example of our mixture. Okay, so basically how we are going to achieve that target function is just by adjusting the parameters W and B we talked before, and that adjusting process is how we called is the so-called learning process of neural networks. Basically, we think the neural network is trying to learn something when it's adjusting the parameters in the neural network, and the way to tell the neural network whether it's doing right or doing wrong are based on two part of things. First of all, the cost of function, and the second thing is the minimization algorithm. About the minimization algorithm, we will talk about in chapter 4. So next thing we will talk about the first part of learning process, the cost of function. And the first one is the supreme error function. For some, if you are familiar with analysis, you should be familiar with supreme. And the supreme function is basically, the supreme error function is, there is an example. So a neural network that takes the input from 0 and 1 will learn a continuous function that is from phi 0, 1 to the real number, say that you can say, okay, it maps 0 to 0, and it maps 1 to 0, and maybe someplace, you know, at 0.5, it maps the things to maybe 10,000, and you want to learn, okay, what is that function? What is that function really is? And if f is the input-output mapping, as we said before, then the cost function is, okay, see this, the cost function we write it as CWB because it, of course, is parametered by W and B, those two internal parameters of the neural network. And here is the absolute value between Fx and the phi x, basically. Okay, given x, say that our fx maps 0 to 1, and the desired one will map 0 to 0, then the distance, the absolute value between them are 1. So sorry, I maybe focus on something that it actually represents the distance, and the sub tells you, okay, these are the things I know from 0 and 1. I want to find the largest distance between them, right? This can be some kind of measurement of how good I'm learning things. And in practice, there are endpoints of target function known. Say that, like my forward example, I know the target function will map 0 to 0 and map 1 to 0 and map 0.5 to 10,000 or somewhat or other things. So there are endpoints known, but the rest of things are unknown. And that is how in practice the neural networks works, because it won't take the infinite many points to learn about things. So these endpoints known already are called the training site, and in that sense, the cost function will become, okay, the max, the max value of those endpoints known, and the corresponding between the input-output mapping and the target value. So that is the cost function. Sorry, here I think I made some mistake. This one should be same as the upper one. Okay, so that is cost function. And what we are trying to do through that process, you know, the cost function. So have a point will let you, you can calculate the cost function, you can calculate the value. What we are trying to do is just to find the minimize of that cost function. We want to find the smallest value. Why? Because like I said already, f the absolute value between f and phi are somewhat a distance. It measures what? It measures how close you are to the correct answer. You know, f is what you guess. F is what you guys is what you are trying, and phi is what you want to do. So now you need to know, okay, how close I'm at. Is it really far, or is it somewhat far, or is it like just a little bit far, or it's really close? I don't know. I need the cost function. If if you're really familiar with operational research and optimization, you should know, okay, everything. There's nothing more than the minimization of cost function. Of course, in some cases, we will maximize that function because the special meaning of the cost functions, but most of the time we try to minimize it. And how to find that minimized point is always interesting. That is something we will talk in the chapter 4, that we will say, okay, this is how we find the minimized point and why it works. But for now, definitely you should know what is the function I need to find the minimize. What is minimum point? What is the function I need to find the minimum point? And that is error function. Without knowing error function and without having a correct meaning for error function, it is a little bit rootless to talk about the following things, such as how to find the minimum, because, you know, even though you find the minimum, that is still meaningless, right? So let's head into next error function, because as here you may see the supreme of these these n pair of values, the maximum of those n values may be a little bit hard to find the smallest value, that you do not know what is the next direction I should guess f. But the next one will show you some fancy properties to support you that give you a little bit idea on how we will find the minimum thing. So the next one, L2 arrow function. About the L2 space, we have talked a little bit before, and in this chapter, we are still using the most basic things about L2. So I decided to still halt a little bit to not go too deep into what is L2 space. So let's look at the arrow function. Assume the input of neural network is x between 0 and 1, and the target function is still phi from 0 and 1 to the real number. It's square integrable. See the difference? It's square integrable. And if f is the mapping, as we said before for many times, then the cost function that measures distance in L2 norm. L2 norm is something we mentioned before, right? L2 norm between the output and the target is, okay, the CWB, the cost function equals the integral from 0 to 1, f minus phi to the square dx. That is how it works. That is what is L2 arrow functions. And you know, as we said before, it is a distance, and L2 norm somewhat in the meaning of L2 space, it is the distance between two things, between actually the output and the target. Still, it shows you how close you are. Your output is from the target. Is it really far? Is it really close? Or is just okay? All right. And in practice, we can't know every point. We can't know infinite many points. But so here are n points known, and say still it maps 0 to 0, it maps 1 to 0, it maps maybe 0.5 to 10,000 to a million to a billion, whatever it is. Then the cost function is the square of Euclidean distance in Rn between f and z. That is really amazing. You see the Euclidean distance in Rn. So basically the cost function is the Euclidean, or that is also the L2 norm, f minus z to the square in Rn, and x is a vector, x1 to xn, and z is also a vector, z1 to zn. So here, you need to know what? You need to know the cost function here is smooth. Is smooth, it means it's continuous, and there's no sharp point, and so generally it indicates something. It means it can be minimized through the gradient descent method. So what is gradient descent method? In your calculus 3, I assume you must know what is gradient and what is gradient descent. You know, just go through the gradient direction. So say that we have a plane. And you have a you have some kind of curve that is convex, that is smooth going up and going down. Say, just think about y equals to x squared in your mind, and draw the figure of that. So here, what is a gradient descent? If you start at some point, you want to find the minimum point, which is at 0. What do you need to do? You need to go to the gradient well, actually, that is not the gradient because it's in 2 dimension instead of 3 dimension or higher dimension. But generally, you know, just go through the right direction with a step length, and as long as you find the proper step length, your result will be really close to 0, right? If you start with you are starting at x equals to 2, and you choose a step length of 2 each time, you will go to maybe you start at x equals to 8, you will go to 6, you will go to 4, you will go to 2, you will go to 0, and then you found, okay, the curve of the function, the slope of the function is 0. That is excellent. That means you find the minimized point. And the same thing happens in Rn, just in a more advanced linear algebra perspective, but the idea is still the same as long as you find the correct step length, as long as you find the proper step length, you will find satisfying enough results. All right, that is the L2 function. And I would like to give some more geometric interpretation of that. So for any fixed vector x, the mapping from WB to fx represents a hypersurface in Rn that parametrics by by WB. And the cost of function represents the Euclidean distance between the given point Z and a point on the hypersurface. Sorry, that is not one this hypersurface, on the hypersurface. It's really easy to make typo. And the cost is minimum when the distance is the shortest, which is the point fx is the orthonormal projection of Z onto the hypersurface. So that is, for me, it's excellent. If you know something about linear algebra, you know there are many ways for you to calculate the orthonormal projection from one point to a surface, and that is excellent. You may have a question, what is hypersurface? I don't know, most mathematicians or computer scientists learn this, or just a math student. I don't really know most what is the class. Most of them learn this terminology, but for me it is the convex optimization. When I read the book on myself, the first lesson I took is definitely if you want to learn about convex optimization, you need to know the definition of what is convex and what is non-convex. So let's still give, let me just give you an example of the in two dimension in plane. So you can think now in your mind, draw a square in your mind, and you can extend one side to infinite length to a line, and what you have is like you will find what that extended line will divide the plane into three parts, right? The left side, or say just one side, and the other side, and the line itself, right? And what you will find is that the convex things, the square here, the area of that square will be totally on one side of the line, but instead it but not going to the other side. So that is how we define convex in the in two-dimensional space in a plane. And when but if you draw a different figure, say if it's non-convex, or say maybe an example is darts, a dart like an arrow, an arrowhead, you will have you can extend two lines and to a line, and you will find, okay, in this situation, not all the area of this darts will be on totally one side of the line, but instead it will both sides will have some area, and that is how we define non-convex in the two-dimensional space. And the hypersurface here is nothing superficial, is nothing fancy, just it's just in Rn. It's just the same idea in Rn, that you have a support plane, and other than the support plane, you will have some other part of hypersurface that support you to determine whether something is convex or not. And because we say here the function is smooth, and it can be that indicates it's convex, and it can be minimized through the gradient descent method. So that means it's convex, and so all the things will be on the one side of the hypersurface. In that sense, it offers you an idea why that point or that given point of vector Z can be also normal projected onto the hypersurface. So if you are really interested in that, I can definitely add something more more to that. But for now, I just think it's not too proper to go too deep into that, because our key things today is what is the error function and the idea of error function, why we need to minimize it. All right. The next part, the mean square error function, the MSE, it is really famous. I think most of the students and major in computer science and mathematics, when they deal with statistics, they will meet the mean square error a lot of time. So let's begin. The mean square error function, what is that? So think about this: given a neural network, the input is a random variable capital X, and the output is random variable capital Y equals to f capital X, and then the network is going to approximate the target random variable Z. The error function measures a proximity between Y and Z. So a good method then is given by the expectation of their square difference, basically the cost function. The cost function here equals to the expectation. This E is the expectation operator of Y minus Z to the square. So in another word, it is the fx minus z squared, the expectation of that. And then the minimization of cost function, this one can be achieved by some minimization algorithms such as the steepest descent method that we will talk about in chapter 4. So in that sense, we will talk it later, but for now you need to know, okay, the minimization algorithm may be a little bit different from what we talked in the forward one, that gradient descent method. So take the different direction. All right. The book gives you several reasons why MSE is so famous, why many mathematicians and computer scientists would like to use MSE. And here I will talk with you a little bit more about them. So first of all, that the square of all square interval random variables from a probability space will form you a Hilbert space that the inner product xy equals the expectation of xy. And this actually defines the norm x square equals to the expectation of x square, and induce the distance between x and y is actually just the distance between x and y, just written it as x minus y. It's easy. And the cost function then in that sense represents the square of a distance. When we can give it some meaning, like we said, like we said before, in the first place, you can see, okay, the supreme error function, it is just the biggest difference, the biggest distance, and here still we get back to distance, just the square of a distance, and that is amazing. That we can just written the cost function as the distance between y and z to the square, just how close your output is to the target function, as we said before for many times, how good you are approximating it and how close you are to the target. That is, amazing. And the minimize the function is just to minimize the distance, because when you put a square to it, you want to minimize the function. Definitely, what you need to do is to minimize the distance. And the definition of the cost function is really easy. The second reason why it's famous is this: it can be really easy to extend to the case when the random variables are known by measurements. So you can consider measurements of random variable x and z, and they are given by x1, z1, xn, zn. So like many times before, we say 0, 0, 1, 0, 0.51 million, whatever. This is known at the as the training side as well, like we said before already. In this chapter, it's a little bit boring because what changes just the form of the error functions and some properties, but the key idea is still the same. You have some training side and you have a mapping. You need to find the distance, find a way to represent the distance between your output and the target, right? And in this case, for practice reason, the case of the cost function is defined by this average. What is that average? See, the cost function equals 1 over n, and sum of the following things. This is basically you have n training side, and you just put them into, and this can be considered as empirical mean of a square difference of y and z. That the computer, it's really easy to calculate this. Actually, the calculation of this is really easy, so that is another good point why mathematicians would like, because some error functions, the theory, how good it is, how excellent it is, but you just don't know how to use it when you want to actually train something, because the definition of calculation is hard to convert, or some other reason. But that is the second reason why mean square error function is is famous. Of course, the book give you a third advantage why MSE is widely used, but that one is related to the information generated by the output and the target function. And I think it is good. It is better to leave this part of things to chapter 6 when we want to closely examine what are the information contained and carried by the neural network and how much information are lost through that process. At that moment, we will show you some excellent things about the MSE, that how that information are related with each other, and you can even just based on one information group and get another one from a probability perspective. I decided to put it there since the content seems more connected with each other with that chapter. All right. So I think that is for now this chapter. This is the not this chapter, but this video. This video is the first video of chapter 3. I decided to divide this chapter into several things because for now we just go through like 1/4 or 1/3 that many content of the chapter. This chapter is really long, and I'm making it several different video is easier for me to make and easier for you to watch as well. So let me introduce you what we will talk in the next few video. In the next video, we will talk about cross entropy, right? We are heading into the information theory of Shannon. We will talk about Shannon entropy and cross entropy, and we will talk about something generated from Shannon entropy, the KL divergence, some other different things, Jensen-Shannon divergence. We will have maximum mean discrepancy. We will have some other cost of functions, and we will introduce you a lot more things about cost of functions and how you measure how close you are to the correct answer using a neural network, using some numerical method and the probability method. And of course, here are a lot more things like the training and the test errors, geometric significance and cost functions, L1, L2 regularizations. These kind of things are what we are going to talk about in the third video of this chapter. It will going up really soon in the future. And thank you so much. That is what we have for now. That is what we are going to do for now. And if you have any question, please contact me, and here are my contact information. Thank you again.